today as possible. So you can do it the way he just did it, or you can go through the equations. So you still need to go through the equations, unfortunately, in the exam. So you know that COP of the fridge equals Qin over W equals Qin over W, Q out minus W over W, which is Q out over W minus 1. So COP of HP minus 1 is 6.7. So effectively, in an ideal system, you just take 1 away from it. But just to prove it again, you know that 1 over efficiency minus 1 equals 1 over 0.13 minus 1 equals 6.7. So do it both ways just to, as a proof. If you see 4 marks for something like this. But yeah. So determine the molar flow rate of the working fluid if the pressure ratio of the isothermal process is 5. Do you remember how to do that? Alright, let's go over it because that way we can just finish the paper as well. So we know Q out equals negative W23, so 23 equals negative RT and the higher temperature log of P3 over P2. Now you know P3 over P2 equals 5. You know how much energy you're putting in, 17 kilowatts, unless I've forgotten to tell you that. Yes, I have. So you need to put in 17 kilowatts, and the warm side is 30 degrees Celsius. Hence, you get 4.19 moles per second. Yeah? Does that make sense? Any questions? Okay. So we can supply only 2 kilowatts of power to run this heat pump. What is the lowest temperature on the cold side of this cycle at which we still achieve the heating requirement? So if we have a power limitation, what is the lowest temperature we can reach? And it's just using the efficiency calculations. So if efficiency equals 1 minus T cold over T hot, and efficiency equals W over Q out, then T cold equals T hot multiplied by 1 minus efficiency equals T hot 1 minus W over W out. So you have 2 kilowatts of energy being put in, and you have 17 kilowatts coming out. So the lowest temperature you can reach is 267.5 Kelvin. It's just balancing algebraic equations. Yeah. Energy balance. The heat pump is used to heat a large swimming pool, which can be treated as a true thermal reservoir. Usually heat pumps are used for swimming pools because they're most efficient and it's the cheapest in the middle of a city. The water temperature, well, the efficient ones. The water temperature is 30 degrees. Use a TS diagram to show whether the heat exchange between the cycle and the water is reversible or irreversible. Briefly explain your arguments. Your argument should also explain why the process you present in the diagram have a specific graph you have chosen. So, this for the cycle, because the cycle temperature remains constant, quite constant. Hence the exact temperatures, right? And the delta S of the cycles are quite similar because, again, that's the whole point of using heat pumps. So let's say this temperature of the swimming pool drops down to 29.7 degrees, heats up to 30 degrees. So when you're doing an ideal system, you assume it never falls below 30 degrees. So the cycle is isothermal by design, water isothermal by definition, i.e. thermal reservoir. So the thinking is the thermal reservoir it remains infinitely hot, or rather, it's infinitely large, if you will. Since the temperature of both processes are the same and exchange heats have the same absolute values but opposite signs, the two entropy changes have the same absolute values but opposite signs. These are all based on ideal assumptions. So you assume the temperature of your heat pump and the temperature of your reservoir are exactly the same, which in reality is impossible because you need that difference in heat to drive the heat exchange. But just for the sake of it, based on the numbers you're given, so 30 degrees, then this is your entropy. Yeah? And that's actually it. and we've done that the other day. So that's pretty much it.